The cosmos is a grand design whose blueprints were lost at the dawn of time. We are now piecing together its hidden architecture, a structure that dictates the fate of everything from the smallest particle to the largest galaxy. By the end of this, you will see the universe not as a chaotic void, but as a readable, elegant construction. Why do the deepest laws of physics seem perfectly tuned for our existence? And what secret signatures are woven into the very first light of creation? How does it feel to realize that reality itself might have a fundamental design? A cathedral of cosmic scale stands before us, its vaulted ceilings made of space-time, its pillars the invisible forces that bind the cosmos. We cannot see the architect's original drawings, yet we feel their presence in the perfect alignment of its structures. This is the profound idea of a universal blueprint, a master plan that has guided the evolution of everything from the first instant to the sprawling galaxies we see today. This concept is not merely science fiction. It resonates from the deepest inquiries of ancient thinkers to the most advanced equations of modern physics. The legendary physicist John Wheeler captured this essence with his famous phrase, "it from bit." He proposed that every particle of matter, every force field, might ultimately be a manifestation of information, that the universe is fundamentally computational, built from an underlying code. This shifts our perspective dramatically. The seemingly fixed numbers that govern our reality, the speed of light, the strength of gravity, the mass of an electron, they start to look less like random constants and more like deliberate settings, fine-tuned parameters written into the blueprint long before the first star ignited. This is where the Anthropic Principle enters the conversation, a simple yet staggering idea. It suggests that the universe we can observe must be compatible with the conscious life that observes it. The constants are so precisely set that even a tiny alteration would render a cosmos of sterile emptiness without galaxies, stars, or planets. The laws themselves, like Einstein's general relativity, possess a breathtaking mathematical elegance. They are not messy rules but the clean, architectural principles from which the cathedral is constructed. So how does this hidden framework touch your own reality? Every time you feel the solidity of the ground beneath your feet or witness the unwavering light from a distant star, you are interacting with the direct consequences of this grand design. The blueprint is not a distant abstract concept. It is the very foundation of your daily experience. With this foundation laid, we are ready to search for the tools that can let us read these faded cosmic plans. Our first tangible clue is written across the entire sky in faint, cold light. This is the cosmic microwave background, the oldest photograph of the universe ever taken. It is the cooled and stretched remnant of the universe's fiery birth, a fossilized echo of the Big Bang that has been traveling through space for nearly 14 billion years. Its discovery in 1965 was a happy accident, a persistent hiss in a radio antenna that turned out to be the universe's background hum. Scientists like George Smoot famously called it the handwriting of God, not for religious reasons, but for the profound information encoded within its seemingly uniform glow. To the most sensitive instruments, this bath of microwaves is not perfectly smooth. It is imprinted with minute temperature fluctuations, tiny ripples of hotter and colder spots. These are not mere imperfections, they are the cosmic seeds from which everything we see eventually grew. These tiny variations in density acted as gravitational anchors. Over eons, matter was drawn to these slightly denser spots, pooling into vast clouds that collapsed to form the first stars, the first galaxies, and the great cosmic web we observe today. Space missions like WMAP and Planck have spent years mapping this fossil light with breathtaking precision, creating a detailed baby picture of the cosmos. The pattern they found is not random. It carries a specific statistical signature that strongly supports the theory of cosmic inflation, a notion that the universe underwent an unimaginably rapid expansion in its first fleeting moments. These ripples are the magnified imprints of primordial quantum fluctuations, tiny jitters in the fabric of spacetime itself that were stretched to cosmic proportions. So what does this ancient blueprint tell us about the universe's fundamental design? The specific characteristics of these ripples reveal the universe's exact age, its overall shape, which appears to be flat, and its precise composition, telling us exactly how much of the cosmos is made of ordinary matter, and dark energy. It is our first and most direct look at the universe's original specifications. But this fossil light is just the first page of the blueprint. To understand the full design, we must now investigate the invisible scaffolding that holds this entire cosmic structure together. That ancient light gave us the universe's initial conditions, but the blueprint's full grandeur is only revealed by what grew from those seeds. If we could step back and view the cosmos on the largest scales, we would not see a random scattering of stars. Instead, we would witness a vast, intricate architecture, a cosmic web of staggering proportions. This is the second major clue in our investigation, the large-scale structure of everything. Galaxies are not isolated islands. They are strung along immense filaments of dark matter, like luminous pearls on invisible strings. These filaments stretch across billions of light years, connecting at dense nodes where thousands of galaxies swarm in massive clusters. Between these structures lie the cosmic voids, unimaginably vast and nearly empty regions of space. This entire sponge-like structure is a direct physical manifestation of the universe's hidden design, a fossilized record of gravitational forces playing out over cosmic time. How did this web form? It began with the tiny ripples in the cosmic microwave background. Those slight over-densities acted as anchors for dark matter, the invisible scaffolding of the cosmos. Though it does not emit, absorb, or reflect light, dark matter's gravitational pull is the primary architect of this web. It collapsed first into a network of filaments, and ordinary matter, the gas that makes stars and planets, simply flowed along this pre-existing framework, pooling into the galaxies we can see. Groundbreaking projects like the Sloan Digital Sky Survey have spent decades mapping the positions of millions of galaxies, creating a three-dimensional chart of this cosmic geography. The result is a map that looks eerily like a neural network of the cosmos, or the froth on an ocean wave. This is not a coincidence. It is the signature of physics operating under a specific set of rules. When we compare this observed map to supercomputer simulations of cosmic evolution, the match is stunning. The simulations, which are based on our understanding of gravity and the properties of dark matter, successfully reproduce the web, the clusters, and the specific statistical distribution of the voids. This tells us we are on the right track. The patterns in the cosmic web are a second, powerful confirmation of the initial blueprint written by inflation. They also reveal the nature of dark matter itself. The fact that the web formed in this specific filamentary way tells us that dark matter must be cold and slow-moving, allowing it to clump together from those tiny seeds. This cosmic architecture is not static. It is a dynamic structure that dictates the motion of everything within it. Entire galaxies are being pulled along these invisible rivers of dark matter, on collision courses with their neighbors, shaping their destinies over billions of years. This great cosmic dance, governed by the web's gravitational pull, even influences the ultimate fate of the universe's expansion. We have now seen the blueprint's large-scale design, from the initial ripples to the vast web. But to read the finest print, we must shrink our perspective down to the very smallest building blocks of reality. Fritz Zwicky, studying the Coma cluster of galaxies in the 1930s, noticed something deeply unsettling. The galaxies were moving so fast that the cluster's visible mass, all the stars and gas he could see, should not have been able to hold them together. The cluster should have flown apart. He concluded there must be something else there, something massive and completely invisible. He called it Dunkel Materie, dark matter. Decades later, Vera Rubin provided irrefutable proof. By measuring how fast stars orbit the centers of spiral galaxies, she found a stunning contradiction to Newton's laws. Stars far from the galactic core were orbiting just as fast as those near the center. According to the gravity of the visible matter alone, these outer stars should have been flung off into the void. The only explanation was that each galaxy is embedded within a vast, massive halo of something that does not shine, a spherical cloud of dark matter whose gravity grips the stars, keeping them from escaping. This invisible substance is not a minor component. For every ounce of the familiar atoms that make up our bodies and our world, there are about 5 ounces of dark matter. It is the universe's primary building material, the hidden framework upon which everything luminous is built. Think of a city seen at night from an airplane. You see the glittering lights of buildings and streets, but you cannot see the ground, the foundational rock and earth upon which the entire city rests. The lights are the stars and galaxies, the visible universe. The unseen ground, the continent-scale foundation, is dark matter. Without its immense gravitational wells, ordinary matter would never have pooled together densely enough to ignite the first stars. Galaxies as we know them simply would not exist. We are here because this cosmic scaffolding exists. So what is it made of? The leading hypothesis points to a class of theoretical particles known as WIMP, or weakly interacting massive particles. These particles would be heavy by subatomic standards and would interact with normal matter only through gravity and the weak nuclear force, making them extraordinarily difficult to detect. The hunt for them is one of the greatest experimental challenges in science. Deep underground, in mines shielded from cosmic rays, vats of ultra-pure liquid wait for the once in an eon bump of a dark matter particle. In powerful particle colliders like the Large Hadron Collider, scientists smash protons together at nearly the speed of light, hoping the immense energy will conjure these elusive entities into existence for a fleeting moment. Yet so far the detectors remain silent. This profound silence is itself a clue. It forces us to ask a more radical question. What if dark matter is not a single, simple particle? What if it represents an entire hidden sector of physics, a shadow universe with its own rich structure and laws, interacting with our own only through the faintest whisper of gravity? Unraveling this mystery is not just about identifying a missing component. It is about reading the next chapter of the cosmic blueprint, a chapter that dictates the ultimate fate of all structure. The gravitational pull of all this dark matter is relentlessly tugging the universe back together, slowing its expansion. Its precise amount and distribution will determine whether the cosmos collapses in a big crunch, expands forever into cold isolation, or finds some precarious balance. We have mapped the blueprint's large-scale structure and felt the presence of its invisible architect, but to understand the design at its most fundamental level, we must now journey to the other extreme of scale, to the bizarre rules that govern the very small. But just as we mapped the invisible scaffolding of dark matter, a far more mysterious force was waiting in the shadows of our data. In the late 1990s, two independent teams of astronomers made a discovery so shocking it overturned our most fundamental assumption about the cosmos. By observing distant stellar explosions known as Type 1, a supernova, they found that the universe is not just expanding, its expansion is accelerating. It is speeding up. This was like tossing a ball into the air and watching it fly away from you faster and faster, defying the pull of gravity. This revelation earned them the Nobel Prize and introduced us to the blueprint's most enigmatic component, dark energy. The supernova, which should have appeared a certain brightness based on their distance, were consistently dimmer than expected. The only logical explanation was that these cosmic mile markers had been pushed farther away than anyone predicted, evidence that the fabric of space itself is stretching at an ever-increasing rate. What could possibly be causing this? The leading candidate is a concept Einstein himself once proposed and then discarded: the cosmological constant. This is not a substance flowing through space, but rather a property of empty space itself. Think of the purest vacuum you can imagine, a volume containing absolutely nothing, no atoms, no light, no particles. According to our best theories, even this perfect void possesses a fundamental, intrinsic energy. This vacuum energy exerts a negative pressure, a sort of cosmic repulsion that pushes space apart. This is dark energy, and its effect is to work against the relentless gravitational pull of all the matter, both light and dark, that tries to hold the universe together. The balance between these two titanic forces, the inward pull of gravity and the outward push of dark energy, dictates the ultimate fate of everything. For billions of years, gravity was dominant, slowing the expansion as it sculpted galaxies and clusters. But around 5 billion years ago, as the universe grew larger and more diffuse, dark energy took over. Its influence is now the dominant force in the cosmos, and it will only grow stronger as space continues to expand. So what does this mean for the long-term future? If dark energy remains constant, as the cosmological constant suggests, the acceleration will continue unabated. In 1 trillion years, all galaxies outside our own local group will have been pushed beyond the cosmic horizon, their light forever too faint to reach us. The universe will become a vast, cold, and lonely place, with isolated islands of stars drifting in an ever-darkening and empty sea. This is known as the Big Freeze, a slow and silent heat death. But what if dark energy is not constant? Another, more unsettling possibility is that it could grow stronger over time. In this scenario, called the Big Rip, the accelerating expansion would eventually become so violent that it would tear apart everything, first galaxy clusters, then individual galaxies, then stars, planets, and finally the very fabric of space-time and atoms themselves. The cosmic blueprint would be shredded. This profound mystery, whether dark energy is stable or dynamic, is now one of the most urgent questions in science. How does this repulsive force fit into the grand architectural design? Its existence suggests that the blueprint is not a static, one-time plan. It is a living document with forces that can change their influence over cosmic epochs. The balance between dark matter's construction and dark energy's dissolution is the central drama of our universe's story. We have now journeyed from the largest scales of the cosmic web to the fundamental forces shaping its destiny. But to truly understand the architect's hand, we must look for the deepest layer of the blueprint, written not in forces or matter, but in the very information that defines reality. These fundamental constants are the universe's ultimate fixed points, the unchangeable numbers written into the very source code of reality. Think of the fine structure constant, a number close to 1/137th that dictates the strength of the electromagnetic force. It controls how tightly atoms hold onto their electrons, how stars burn their nuclear fuel, and even the very structure of molecules. It is a pure, dimensionless number, and its value appears utterly arbitrary. Yet if it were just a few percent larger or smaller, the consequences would be catastrophic. A slightly stronger electromagnetic force, an atomic nuclei would repel each other so fiercely that nuclear fusion in stars would be impossible. A slightly weaker force, and atoms could not bond together to form the complex molecules necessary for life. The same breathtaking precision applies to the mass of the electron, the strength of gravity, and the other fundamental parameters. They are all dialed in with an inexplicable precision, as if set by a master engineer. This is the fine-tuning problem, and it presents a profound mystery. Why does our universe possess this specific, seemingly curated set of numbers that allows for stars, planets, and ultimately, us? One compelling answer lies in the concept of the multiverse. If our cosmos is just one bubble in an infinite, frothing sea of universes, each with its own random set of physical constants, then it is no surprise we find ourselves in one of the rare, habitable ones. In most universes, the numbers would be wrong, leading to a quick, sterile death. Only in the finely tuned ones could observers ever arise to ponder the question. The alternative is more radical, suggesting these constants are not random at all. Theories like string theory propose that they are the inevitable outcome of a deeper, more elegant reality, one that might involve tiny, curled-up dimensions existing at every point in space. The quest for a theory of everything is the ultimate archaeological dig into the cosmic blueprint, an attempt to find the single, underlying principle from which all these seemingly arbitrary numbers naturally flow, revealing why the universe had to be built this way. These constants are the final, deepest signature of the architect, the precise numerical values that had to be chosen to bring a living, thinking cosmos into being. The universe's grand design did not emerge slowly. It was drafted in a single, breathtaking burst of exponential creativity. In the first sliver of a second after the Big Bang, the cosmos underwent a growth spurt so violent it defies human intuition. This was the inflationary epoch, a moment when space itself expanded faster than the speed of light, smoothing the primordial chaos into a coherent canvas. Think of an artist rapidly stretching a tiny, crumpled piece of paper to the size of a continent. Every tiny wrinkle and imperfection is smoothed away, leaving behind a vast, flat surface ready for detail. This is what inflation did for our universe. It solved profound mysteries like the horizon problem, which asks why regions of space too far apart to have ever been in contact somehow share the exact same temperature and properties. Inflation explains this by revealing they were once neighbors, intimately connected before the great stretching tore them apart. It also resolved the flatness problem, the puzzling observation that our universe's overall geometry is perfectly balanced, neither curving back on itself nor flying apart uncontrollably. Inflation naturally flattened the cosmos, much like blowing up a balloon to an immense size, makes its surface appear flat to a tiny ant crawling upon it. But this smoothing process was not perfect, and that imperfection was its greatest gift. The empty vacuum of space during this period was not truly empty. It was filled with a hypothetical energy field called the inflaton field, and this field was fizzing with quantum fluctuations, tiny, unpredictable jitters at the smallest possible scale. As the universe inflated, these infinitesimal ripples in the inflaton field were stretched to macroscopic proportions. They became the subtle variations in density, the blueprint's first pencil marks that gravity would later use to build galaxies, stars, and us. This was the primary drafting phase, the moment the initial conditions were literally printed onto the fabric of the cosmos. The predictions born from this idea have been stunningly confirmed. Our most sensitive probes of the cosmic microwave background reveal the specific pattern of hot and cold spots that inflation demands, and they confirm the universe's overall flat geometry with incredible precision. We are essentially looking at the magnified signature of those primordial quantum jitters, yet profound mysteries remain. What was the true nature of the inflaton field? What specific trigger started the inflationary expansion, and what mysterious mechanism caused it to suddenly stop, converting its immense energy into the hot soup of particles of the traditional Big Bang? Could there be other, fainter signatures of this event, perhaps imprinted as gravitational waves on the cosmic microwave background, waiting for a future generation of telescopes to discover? Understanding inflation is like uncovering the architect's very first sketch, a frantic, brilliant moment of rapid design that defined the entire structure to follow. And just as this epoch imprinted its pattern on the cosmos, another, equally fundamental layer of the blueprint was being written, not in the fabric of space, but in the very information that constitutes reality itself. But what if the very space we inhabit, with its three vast dimensions of depth and breadth and height, is itself an illusion? The holographic principle proposes exactly this, a radical idea that our universe, in all its apparent complexity, might be a magnificent projection from a simpler, two-dimensional reality. This is not science fiction, but a serious concept born from the strange physics of black holes. When scientists like Jacob Bekenstein and Stephen Hawking calculated that the maximum information a black hole can contain is not proportional to its volume, but to the area of its event horizon, it created a paradox. How could a three-dimensional object's information content be limited by its two-dimensional surface? Physicists Gerard T. Hooft and Leonard Susskind took this idea and ran with it, proposing that this is not a special property of black holes, but a fundamental feature of our universe. The holographic principle suggests that all the information needed to describe everything within a volume of space, every star, every planet, every one of us, is actually encoded on a distant, two-dimensional surface that surrounds it, like a cosmic DVD. The three-dimensional world we experience is just a holographic projection of that data. Think of a security hologram on a credit card. It appears to have depth and dimension, yet all that information is stored on a flat, two-dimensional surface. The holographic universe theory suggests our reality operates on a similar but vastly grander principle. If this is true, it means the true, fundamental blueprint of the cosmos is not written in three dimensions. It is a simpler, more compact code inscribed on the boundary of space itself. This overturns our most basic intuition. We naturally assume a larger box can hold more things, and therefore more information, than a smaller one. But the holographic principle states that the maximum information any region can ever contain is defined by its surface area. A universe-sized sphere has a finite amount of information, and that information is all stored on its outer shell. What does this mean for our understanding of reality? It implies that the solidity of the world around us, the very feeling of locality, where objects are definitively here and not there, is an emergent property. It is not fundamental. The deepest layer of reality might be a vast, interconnected web of information where concepts like distance are not primary. Researchers are actively searching for evidence. Some are analyzing the patterns in the cosmic microwave background, looking for subtle statistical anomalies that could be the pixelation of our cosmic projection. Others are designing tabletop experiments to probe the extreme limits of spacetime, seeking the graininess that a holographic universe would predict. If confirmed, the holographic principle would represent the ultimate simplification of the cosmic blueprint. The grand cathedral of space-time, with all its dark matter scaffolding and dark energy expansion, would be revealed as a breathtakingly detailed illusion, projected from a fundamentally simpler two-dimensional reality. This forces us to ask, if the universe is a hologram, what or who is the projector? These vibrating strings are the universe's ultimate building blocks, replacing the idea of dimensionless points with loops of pure energy. Each string is unimaginably small, so tiny that if an atom were enlarged to the size of our solar system, a string would be no larger than a tree on Earth. The music of the cosmos is not made by stars or galaxies, but by the distinct vibrational patterns of these strings. One specific resonance might create a quark, another an electron, and a different, more complex vibration could produce the photon, the particle of light. In this framework, every force and every particle in existence is unified under a single concept, a tiny, oscillating strand of energy. This elegant idea, known as string theory, represents humanity's most ambitious attempt to read the final draft of the cosmic blueprint, seeking to weave Einstein's theory of gravity seamlessly into the quantum world of the very small. To achieve this mathematical harmony, the theory demands a startling revision of reality itself. Our familiar world of three spatial dimensions is not enough. The equations of string theory only work if the universe has extra, hidden dimensions, curled up into shapes so minute we never notice them. Think of a garden hose seen from a great distance. It appears to be a simple one-dimensional line, but as you move closer, you discover it has a second dimension, a circular cross-section curled tightly around itself. The universe, according to string theory, may be similar. At every point in our three-dimensional space, there could be 6 or 7 additional spatial dimensions, compactified into a complex, intricate shape. The specific geometry of this hidden dimensional landscape is everything. This is where the cosmic blueprint is finally written. The shape of these extra dimensions, known mathematically as a Calabi-Yau manifold, dictates the laws of physics we observe. The number of holes and twists in this manifold, its precise topology, determines the number of particle families, the strengths of the fundamental forces, and even the value of the fine structure constant. The reason our universe has its specific set of rules is because the extra dimensions are curled into one particular, stable shape out of a near infinite number of possibilities. Finding that one correct Calabi-Yau shape is the grand challenge, like searching for a single, unique snowflake in a blizzard that encompasses all of reality. This leads to a staggering, and for some troubling implication, the string theory landscape. If there are an astronomical number of ways for these extra dimensions to curl up, then there could be an equally vast number of possible universes, each with its own unique physical laws. In most of these universes, the constants would be wrong for life. We simply live in one of the rare, habitable ones where the dimensional geometry allowed for our existence. This offers a potential explanation for fine-tuning, but it also suggests our universe's blueprint might be just one page in an infinite cosmic library. The quest to prove string theory pushes the very limits of human ingenuity, seeking fingerprints of these extra dimensions in the aftermath of the Big Bang or in the intense energy of particle colliders. It is a search for the fundamental language in which the architect wrote the plans, a language not of words but of geometry and vibration. Our universe's specific laws might simply be local ordinances. This is the staggering implication of the multiverse hypothesis, a vision of reality where our cosmos is a single bubble in an endless, frothing sea of universes. Each bubble in this grand cosmic foam could have its own unique physics, its own random selection from a near-infinite catalog of possible designs. In one universe, gravity might be so strong that stars burn out in a cosmic instant. In another, the nuclear forces could be too weak to form atoms at all. Some universes might blossom with extra, unfolded spatial dimensions, while others could operate under entirely different forms of logic. The blueprint we have been so carefully deciphering, with its precise constants and elegant equations, would not be a unique master plan. It would be just one set of working drawings, one possible configuration that happened to produce a stable, long-lived and habitable cosmos. The profound fine-tuning we observe would have a simple, if humbling, explanation. We do not live in a specially designed universe. We simply inhabit one of the rare bubbles where the numbers are right for life to emerge and ask the question. This idea flows naturally from the theories we have already explored. Eternal inflation suggests that the rapid expansion of the early universe never truly stopped, but continues endlessly in a background metaspace, continually spawning new bubble universes with random properties. Meanwhile, the vast landscape of possible solutions in string theory provides a mathematical library of 10 to the 500 or more potential universes, each corresponding to a different way for the extra dimensions to curl up. The multiverse concept transforms our search for a single, elegant blueprint into something entirely different. We are no longer archaeologists looking for the one true architect's original document. Instead, we are explorers in an infinite metropolis, holding a map of our own neighborhood and trying to understand why its zoning laws allow for parks and skyscrapers, while other districts are barren wastelands or realms of chaotic energy. This expansion of scope is intellectually breathtaking, but it comes with a profound scientific challenge. How can we ever test a hypothesis about other universes that are, by their very nature, permanently disconnected from our own? Any signal from another bubble universe would be lost in the unimaginable void between them. Critics argue this makes the multiverse untestable, and therefore more a philosophical concept than a scientific one. Proponents, however, search for indirect evidence. They look for any unique signature our universe might carry from a long-ago collision with another bubble, perhaps an odd pattern in the cosmic microwave background. They also suggest that the same reasoning we use to understand our place in the cosmos applies here. We do not find it unscientific to talk about other galaxies, even though we cannot visit them, because we understand the principles that govern them. If a multiverse is the natural consequence of our best theories of inflation and quantum physics, then to ignore it would be to ignore the full implications of the cosmic blueprint we are trying to read. The multiverse does not necessarily make our universe less special, but it does redefine the nature of that specialness. The elegance we find in our local laws is no less beautiful, and the mystery of our existence is no less profound. It simply suggests that the grand design is far more expansive, creative, and perhaps more chaotic than we ever dared to imagine. The smooth, curving fabric of spacetime described by Einstein and the fuzzy, probabilistic world of the quantum have always been at odds. One paints a grand, continuous landscape, the other a frenetic, pixelated dance. Unifying them into a single theory of quantum gravity is the ultimate challenge, the final act of reading the blueprint to understand the very material from which the cosmos is made. This is not just about adding another piece to the puzzle, it is about discovering what the puzzle is actually made of. One profound approach, known as loop quantum gravity, takes this idea literally. It proposes that space itself is not a smooth, infinitely divisible backdrop. Instead, it is woven from a fabric of tiny, discrete loops, one-dimensional threads of space that form a network of relationships. Imagine the universe not as a blank, continuous canvas, but as an impossibly fine piece of chainmail armor, with each interlocking ring representing a single quantum of space. These loops are the atoms of geometry, the indivisible building blocks from which volume and area are constructed. The theory then describes how this network evolves over time. The history of this quantum spacetime is not a smooth movie, but a sequence of distinct frames, a frothing, bubbling structure known as a spin foam. In this view, the familiar, continuous spacetime we experience every day is an emergent property, a large-scale illusion that arises from the collective behavior of these countless discrete connections, much like the smooth surface of a pond emerges from the chaotic interactions of trillions of water molecules. This provides our first potential microscopic description of the cosmic architecture, a blueprint written not in forces or particles, but in the fundamental relationships of quantum geometry. If space is truly granular at this fantastically small scale, could we ever detect its graininess? One promising avenue looks to the farthest reaches of the cosmos. When immensely powerful gamma-ray bursts explode across the universe, they send photons of vastly different energies on a billion-year journey to our telescopes. If spacetime is a quantum foam, these different photons might interact with its fine structure in subtly different ways. A high-energy photon could potentially feel a slight drag compared to a lower-energy one, causing a tiny, cumulative delay in its arrival time. While we have not yet found definitive proof, the search for this delay is like trying to hear the faint rustle of a cosmic fabric, a whisper of its true, grainy nature. This quantum view of gravity also radically reshapes our understanding of the universe's birth. In the standard Big Bang story, we are pushed back to a singularity, a point of infinite density where the laws of physics break down. But in loop quantum gravity, there is no singularity. The quantum nature of spacetime prevents the universe from collapsing into an infinitely small point. Instead, the theory suggests a big bounce, a moment where a previous contracting universe reached a minimum size and then rebounded into the expansion we see today. This paints a breathtaking new picture of the initial conditions, where the blueprint itself might be cyclical, forever being rewritten. Unifying gravity with the quantum world is the final step in the ultimate reverse engineering project. It is the quest to understand not just the architect's drawings, but the very substance of the parchment and the properties of the ink. This knowledge would complete our picture, revealing the fundamental materials and the precise construction techniques used to build everything we know. This perfect calibration of the cosmic constants leads us to a profound and deeply personal question. Are we merely lucky inhabitants of a universe that happened to get the numbers right? Or is there a deeper connection between the existence of life and the architecture of the cosmos itself? This is the heart of the Anthropic Principle, a concept that forces us to confront our own place in the grand design. In its simplest form, the weak Anthropic Principle is a statement of obvious yet staggering logic. It says that we, as conscious observers, can only find ourselves in a universe that has the necessary conditions for our existence. We could never be asking these questions in a cosmos where the electromagnetic force was too weak to bind atoms, or where gravity crushed stars before they could ignite. Our very presence acts as a filter, selecting for this specific, habitable reality out of a vast range of possibilities. The strong Anthropic Principle takes a much more provocative stance. It proposes that the universe must have properties that allow life to arise within it. This version edges toward the idea of a blueprint with a purpose, a cosmos that is in some sense compelled to produce observers. It does not explain how the constants were set, but it suggests that their values are not a random accident. They are a prerequisite for the story we find ourselves in. When we pair this with the multiverse hypothesis, a powerful explanation emerges. If an infinite number of universes are bubbling into existence, each with its own random set of physical laws, then the vast majority will be stillborn or sterile. In some, gravity will be too strong, causing a swift big crunch. In others, atoms will never form. We do not live in a specially designed universe. We simply reside in one of the extraordinarily rare bubbles where all the countless dials happen to be turned to the just right settings for complexity and life. This is not a design flaw, but a statistical inevitability. Our cosmic address is not special, it is merely necessary. Critics rightly point out that this can feel like a cop-out, a way to explain away fine-tuning without truly explaining it. Calling it a selection effect does not tell us why the dials exist in the first place, or why the range of possible values allows for life at all. Yet for its proponents, the Anthropic Principle is an essential piece of the puzzle. It recalibrates our expectations. We should not be surprised to find ourselves in a universe that looks finely tuned, because we could not exist in any other kind. It forces us to ask whether the presence of an observer is a random byproduct of the cosmic machinery, or if it is a fundamental feature the entire structure was built to accommodate. Does the blueprint require a reader to give it meaning? The answer reshapes our understanding of everything, from the immense cosmos to our very own consciousness. These gravitational abysses present a terrifying puzzle for our understanding of the cosmic blueprint. A black hole is a region where space and time are so warped that the future itself points relentlessly inward. Once something crosses the boundary known as the event horizon, it is, according to Einstein's general relativity, gone forever, its information lost to the rest of the universe. This creates a fundamental conflict with quantum mechanics, which holds that information is never truly destroyed. You can burn a book, but in principle, if you could collect every single smoke particle and ash, you could reconstruct its every word. Quantum physics insists the universe is similarly meticulous, preserving the history of every particle. Stephen Hawking's revolutionary calculation shattered this principle. He showed that black holes are not completely black. Due to weird quantum effects at the very edge of the event horizon, they slowly leak a faint glow of radiation. Over eons, this Hawking radiation causes the black hole to lose mass and eventually evaporate, vanishing completely. And if the black hole disappears, what happens to all the information about the stars, planets, and atoms that fell in? Hawking's math initially suggested it was irretrievably erased, a cosmic deletion that threatened to unravel the logical foundation of physics. This is the black hole information paradox, a glaring conflict between our two most successful descriptions of reality. Resolving it forces us to rewrite the rules of the blueprint itself. One of the most compelling solutions comes directly from the holographic principle. It proposes that when an object falls into a black hole, it does not simply vanish. Instead, all the information that defined it, its quantum properties and unique identity, is not stored in the inaccessible interior. It is perfectly encoded, scrambled, and imprinted onto the two-dimensional surface of the event horizon, like data being burned onto a DVD. The three-dimensional object is gone, but its complete description remains preserved on the boundary. This means the black hole's surface area, not its volume, defines its ultimate information storage capacity. The holographic universe idea suggests this is not a special case for black holes, but a fundamental law for all of space. Another possibility is that the information is not lost, but slowly and chaotically released back into the universe through the Hawking radiation itself. The radiation would not be purely random, but would carry subtle, encrypted imprints of everything that fell in. The evaporation process would be the most complex decoding operation imaginable, releasing the universe's archived data back into circulation. Black holes thus become the ultimate extreme laboratories, testing grounds for theories of quantum gravity. They are not destructive monsters, but perhaps the most perfect and secure archival systems in the cosmos, enforcing the rule that information, the most fundamental currency of reality, must be conserved. This suggests a profound feature of the cosmic blueprint, that its data integrity is absolute. No detail, from the birth of a star to the fall of a single atom, is ever truly erased. It is merely transformed, stored, and potentially retrievable, woven forever into the fabric of space-time. Hidden within the cosmic code is a love for elegant patterns, a deep-seated preference for symmetry that governs everything from the spin of an electron to the whirl of a galaxy. This is not just an aesthetic choice, it is a fundamental structural rule of the blueprint. Think of a perfect snowflake, its six-fold pattern repeating with flawless precision. This kind of symmetry, where an object looks the same after a rotation or a reflection, is a tiny echo of the profound symmetries woven into the laws of physics themselves. The universe operates on the principle that the laws of physics are the same everywhere and in every direction. Rotate an experiment in empty space or perform it on a Tuesday instead of a Monday, and the underlying rules do not change. This consistency is not just convenient, it is generative. These continuous symmetries directly give rise to the conservation laws that keep the cosmos orderly. The fact that the laws of physics are the same at every point in space leads directly to the conservation of momentum. The fact that they are the same at every moment in time guarantees the conservation of energy. These are not separate rules, they are the inevitable offspring of cosmic symmetry. Delving deeper, we find the engine of the standard model of particle physics is powered by something called gauge symmetry. This is a more abstract kind of invariance, a freedom to change our description of a particle field in a certain way without altering any observable outcome. It sounds technical, but its consequence is breathtakingly simple. The requirement that these symmetries hold forces nature to invent the fundamental forces themselves. The photon, the carrier of the electromagnetic force, emerges naturally as the guardian of one such symmetry. The W and Z bosons, which mediate the weak nuclear force, arise to protect another. The forces we experience are the direct result of the universe insisting on preserving its symmetrical nature. Yet, a universe of perfect, unbroken symmetry would be a sterile and simple place. All particles would be massless, zipping around at the speed of light, never clumping together to form atoms or people. The pivotal discovery of the last century was that these beautiful symmetries are often hidden or broken. The Higgs mechanism describes this perfectly. Imagine a banquet table with a perfectly circular seating arrangement. Every seat is identical, the symmetry is perfect. Then the first guest chooses a chair. Suddenly, the symmetry is broken. Every seat is still physically the same, but one has been distinguished. It now has a relationship to the chosen seat. In the early universe, a field known as the Higgs field permeated all of space. As the cosmos cooled, this field settled into a particular value everywhere, breaking a fundamental symmetry. This act gave mass to particles like electrons and quarks as they interacted with this pervasive field, slowing them down and allowing them to form the complex structures we see today. Symmetry breaking is the creative act that allowed richness to emerge from perfect order. This powerful idea drives the quest for a grand unified theory, one of the great unfinished chapters of the blueprint. Physicists are compelled by the notion that the three forces of the Standard Model, the electromagnetic, weak, and strong nuclear forces, were not always distinct. In the universe's first searing moments, at energies beyond our imagination, they were unified under a single, magnificent symmetry. the cosmos was in a state of perfect, hyper-unified order. As it expanded and cooled, this supreme symmetry broke in stages, like a crystal forming from a hot liquid, first freezing out the strong force, then later the weak and electromagnetic forces. Finding the pattern of this breaking, the specific symmetrical group from which our forces crystallized, is the Holy Grail. It would reveal the pristine, original state of the cosmic design, a time of ultimate economy and elegance before the creative chaos of symmetry breaking gave us our world. Why does nature cherish these patterns? The answer may be that symmetry is the most efficient language for a fundamental law to be written in. It is the architect's way of building a universe of incredible diversity from a set of simple, repeating, and beautiful rules. The very first stroke on the cosmic blueprint was the universe's initial state, a set of starting conditions so precise they dictated every structure to come. Think of building a house, but where the first brick you lay determines not just the walls, but the placement of every electrical wire and the very flow of water through the pipes. The Big Bang was not an explosion in space, but the sudden emergence of space, time, and energy itself. The ultimate initial condition was a universe of unimaginable density and heat, yet it possessed a mysterious and profound smoothness. We see this in the cosmic microwave background, that ancient light that glows with nearly the same temperature in every direction we look. This incredible uniformity, this homogeneity, is the foundational layer upon which everything was built. How could regions of the early cosmos that were too far apart to have ever communicated with each other possibly achieve such a perfect thermal equilibrium? This is the horizon problem, and its solution points directly to a dramatic inflationary epoch that stretched a tiny, connected patch into our entire observable universe. Yet this smoothness was not perfect. Those tiny, crucial ripples of varying density were also part of the initial setup, the subtle imperfections that gravity would later use to build galaxies. So where did this specific, highly ordered state come from? Why did the universe begin in such a low entropy condition, a state of exquisite order that gave us the arrow of time, the reason we remember the past but not the future? This is the mystery of the primal setup. Some of the most profound ideas in physics attempt to answer this. The no-boundary proposal, developed by James Hartle and Stephen Hawking, offers a breathtaking vision. It suggests that before the Big Bang, there was no time as we know it. Instead, the dimension of time smoothly transforms into a fourth dimension of space. Much like the North Pole on Earth is a point where the concept of going further north ceases to exist. In this model, the universe spontaneously arises from nothing, not as a singularity of infinite density, but as a finite, self-contained geometry with no edge or beginning. It simply is. Other theories propose a cyclic universe, an endless sequence of big bangs and big crunches, where each cycle's end sets the stage for the next beginning. Or perhaps our cosmos is the result of a random quantum fluctuation in a pre-existing, metastable void, a single bubble that nucleated out of an eternal, higher dimensional landscape. Pinpointing the true initial condition is the ultimate archaeological dig, an attempt to find the very first line the architect drew on a blank canvas. This primal decision, this first stroke, established the rules of the game before the game even began. It set the stage for gravity to pull, for stars to ignite, and for conscious beings to one day look back and wonder how it all started. These elusive ripples in space-time are the ultimate quarry for cosmologists hunting the echoes of creation. Primordial gravitational waves are not the same as the waves detected by LIGO from colliding black holes. Those are the local disturbances of specific cosmic events, while primordial waves are the fossilized tremors from the universe's violent birth, a relic of the inflationary burst itself. According to the theory, the same quantum jitters that created the density seeds in the cosmic microwave background should have also shaken the gravitational field, creating literal ripples in the geometry of spacetime. As inflation stretched the cosmos, these tiny spacetime vibrations were amplified to travel across the entire universe, a permanent, if incredibly faint, hum woven into the cosmic background. Detecting them would be like finding the architect's original signature, a confirmation that the inflationary draft is the correct one. The challenge is that these waves are unimaginably weak after nearly 14 billion years of cosmic expansion. Their signal is not in the temperature of the cosmic microwave background, but in its polarization, the specific direction in which its light waves oscillate. The violent squeezing and stretching of spacetime by these primordial waves would have imprinted a unique, swirling pattern known as B-mode polarization onto the ancient light. Finding this specific curl in the polarization is the smoking gun. Experiments like BICEP at the South Pole stare at a pristine patch of sky, using ultra-sensitive telescopes to search for this faint pattern. The initial announcement of a possible detection in 2014 sent waves of excitement through the scientific community, but it was later shown that cosmic dust within our own galaxy could mimic the signal. This highlights the immense difficulty of the hunt, separating the universe's first whisper from the foreground noise of our galactic neighborhood. Future missions, like the Japanese LED Light Bird satellite, are designed to survey the entire sky with even greater sensitivity, specifically to isolate this elusive signal from all other contaminants. Why is this search worth such immense effort? A confirmed detection would do more than just prove inflation happened. The strength of the B-mode signal directly tells us the energy scale at which inflation occurred. It would reveal the incredible power of the inflaton field, an energy far beyond what the most powerful particle colliders could ever reproduce. This would allow us to rule out whole classes of inflationary models and zero in on the specific physics of the universe's first fleeting moment. But what if, after all our searching, we find nothing? The continued absence of these waves would be a profound puzzle, forcing us to reconsider our most cherished theories. Perhaps inflation did not happen, or it occurred at a much lower energy than we think. Maybe an entirely different mechanism set up the initial conditions of the cosmos. The silence itself would be a message, telling us that the blueprint's first page is written in a language we have yet to understand. This search is the frontier of cosmic archaeology, an attempt to listen for the vibrations of spacetime from the very instant the design was set in motion. Our own lives are defined by the relentless march of time, but physics paints a strangely different picture. The equations of general relativity treat time as simply a fourth dimension, woven into the fabric of spacetime with no inherent direction. In principle, these laws work just as well if time runs backward. This creates a jarring conflict between our lived reality and the fundamental description of reality itself. This is the problem of time, and it strikes at the very heart of our cosmic blueprint. If the universe is a single, self-contained system, what is time ticking against? There is no external clock outside of everything. This leads to a radical idea that the complete blueprint of the cosmos might not be a story that unfolds, but a single, timeless, four-dimensional object, often called the block universe. In this view, the past, present, and future all exist simultaneously, laid out in a vast, static structure. Your birth, your life, and every moment of the cosmos are all equally real, just located at different coordinates in this eternal block. Our powerful sensation of time flowing, of a present moment that is real while the past is gone and the future is not yet, would then be a kind of profound illusion. It would be a perspective we have from inside the block, much like a train passenger experiences a landscape as unfolding, even though the entire track and all its scenery exist at once. This concept finds a startling expression in the Wheeler-DeWitt equation, a foundational attempt to combine general relativity with quantum mechanics. This equation describes the entire quantum state of the universe, but it contains no time variable whatsoever. It simply is. The wave function of the universe is static. If this is correct, then the architect's plan is not a set of instructions for building something, but the finished, eternal building itself, viewed from a God-like perspective outside of time. How then do we explain the vivid, undeniable flow we all experience? The answer may lie in the concept of emergence. Time, as we know it, might not be fundamental. It could be a collective property that arises from the complex relationships between things within the universe. Think of the concept of temperature. A single air molecule does not have a temperature. Temperature is an emergent property of the collective, chaotic motion of trillions of molecules. In a similar way, our experience of a flowing present moment, of cause and effect, could emerge from the intricate quantum correlations between particles and events within the timeless block. Our consciousness, with its limited, sequential processing, might be what carves a path through this eternal structure, creating the story of our lives from a reality where all chapters are already written. This forces us to confront a staggering possibility. Is the cosmic architecture a finished, static structure, or is it an ongoing, dynamic process? The answer may determine whether the blueprint is a single, perfect drawing or an endless, unfolding scroll. The universe began in a state of almost unimaginable simplicity, a hot, dense soup of fundamental particles. Yet from that uniform beginning, everything we know and see emerged. This is the journey from a bare blueprint to a living cathedral, a story written not in detailed instructions, but in the inevitable consequences of a few simple rules. Gravity is the master sculptor in this story. Those tiny ripples in the early cosmos, the ones imprinted on the cosmic microwave background, were the seeds of all structure. Over billions of years, gravity patiently amplified these slight over-densities. It pulled matter together, pooling gas into vast clouds that collapsed under their own weight to ignite the first stars. Those stars then grouped into galaxies, and galaxies themselves were drawn into the great cosmic web. This process of gravitational instability is a powerful, creative force that requires no extra plan. It is a direct, emergent outcome of matter simply responding to the force of gravity over cosmic time. But stars are more than just lights in the void. They are the universe's great factories. Inside their crushing cores, the process of nuclear fusion takes over, performing the next act of cosmic alchemy. It forges the simple hydrogen and helium from the Big Bang into heavier elements like carbon, oxygen, and iron. Then, in their spectacular deaths as supernova, these stars scatter their enriched ashes across space. This stardust becomes the raw material for new stars, for planets, and eventually for the chemistry of life itself. This is how complexity builds, layer upon layer, with each new structure providing the foundation for the next. Planets form from this dust, and on at least one world, those same elements engaged in a chemical evolution of breathtaking intricacy, leading to self-replicating molecules and ultimately to us. This entire hierarchy seems to fly in the face of a fundamental cosmic rule, the second law of thermodynamics. This law states that the universe as a whole is moving toward a state of maximum disorder or entropy. So how can galaxies and life forms, which are pockets of incredible order, possibly arise? The answer is that they are not violations of this law, but a direct consequence of it. A star is a perfect example. It is a highly ordered system, but it maintains that order by burning its nuclear fuel and radiating immense waste heat out into the coldness of space. The star's local decrease in entropy is paid for by a much larger increase in the entropy of the universe around it. The emergence of complexity is a permitted, even an encouraged, side effect of the universe's relentless drive toward overall disorder. The cosmic blueprint, then, is not a detailed architectural drawing marking the position of every star. It is far more powerful and elegant than that. It is a set of simple, generative rules. Give us gravity, nuclear forces, and thermodynamics. Set them in motion within an expanding universe seeded with tiny fluctuations, and the outcome is virtually inevitable. Galaxies will form, stars will ignite and die, planets will coalesce from stardust, and on some of those planets, the conditions will be right for chemistry to become biology. This emergence suggests that we are not a random accident, but a natural expression of the cosmos's latent potential. We are the universe awakening, becoming conscious of itself, and beginning to read the very blueprint that gave it birth. Our entire cosmic survey is conducted from a single, fixed seat in an ever-expanding theater. We are embedded within the very structure we are trying to decode, and this position imposes a fundamental and permanent limit on our vision. The sphere of everything we can possibly see is called the Observable Universe, a bubble centered precisely on us, with a radius of about 46 billion light-years. This is not the edge of the universe, but the edge of our information, the boundary created by the finite speed of light. Every photon that reaches our telescopes has been traveling for a finite time since the dawn of the cosmos, meaning we look out not just into space, but back in time. The farther we peer, the younger the universe we witness, until our most powerful instruments can only see the faint, reddened glow of infant galaxies. But what lies beyond this horizon? The total universe could be vastly larger, perhaps even infinite, and its full architecture remains forever hidden from our direct view. This cosmic horizon is not static, it is shrinking in a relative sense. The accelerating expansion driven by dark energy is constantly pushing distant galaxies away from us at speeds that will soon exceed the speed of light. Not because they are moving through space faster than light, but because the space between us is stretching so rapidly that their light can no longer bridge the growing divide. One by one, these distant island universes will wink out of our observable sky, their light stretched into undetectable radio waves and beyond. In the far future, astronomers in our local galactic group will look out upon an empty, black void, with all evidence of the expanding cosmos and the great cosmic web having vanished beyond an impenetrable curtain. This means we are living in a uniquely privileged era, a cosmic golden hour where we can still see enough of the blueprint to understand its basic design. Our knowledge is therefore provisional, based on a local sample of one. The grand cosmic city might have entirely different districts and zoning laws beyond our horizon, regions where the fundamental constants are different, or where the very nature of dark energy is not a repulsive force but something else entirely. We are like architects trying to understand a boundless metropolis from the view out of one single window. The humility this imposes is profound, reminding us that our entire understanding of reality's design is based on a fragment of the whole. The cosmic blueprint is a document that seems to demand a reader. We are that reader, a product of the very laws we are trying to decipher. This creates a profound loop where the universe has, through billions of years of cosmic and biological evolution, generated conscious minds capable of turning back and questioning the architecture that produced them. Our own consciousness becomes part of the equation, not as a distant observer, but as an active participant in the grand narrative of reality. This connection is most famously and controversially highlighted in the quantum realm. The act of measurement in quantum mechanics is inextricably linked to the observer. A particle exists in a blurry cloud of potential, a superposition of all possible states, until it is observed, at which point it seems to settle into a single, definite reality. This wave function collapse forces us to ask whether consciousness itself plays a role in pinning down reality from a sea of possibilities. While most physicists today lean toward interpretations that do not require a conscious mind, suggesting the interaction with any large measuring device is sufficient, the puzzle remains deeply unsettling. It reveals that at its most fundamental level, the universe does not present us with a single, solid reality, but with a set of potentialities that become concrete through interaction. This blurs the line between the world out there and our perception of it, suggesting that the blueprint might not be fully realized without some form of engagement. This leads to an even deeper philosophical quandary. Are the mathematical laws we so elegantly formulate, from Einstein's general relativity to the symmetries of the Standard Model, genuine discoveries of an objective, pre-existing cosmic plan? Or are they merely clever inventions of the human mind, a set of useful fictions that help us navigate and predict our environment? The fact that mathematics, a product of human reason, is so unreasonably effective at describing the physical universe is, as Einstein wondered, a mystery in itself. It implies a deep resonance between the logic of our minds and the logic of the cosmos, as if both were built from the same foundational principles. The blueprint might be written in a mathematical language, and we, through a long and improbable journey, have learned just enough of its alphabet to begin reading. So, does the architecture of space require an observer to give it meaning? Is the cosmos a finished, self-contained structure whether or not anyone is there to see it? Or does the act of comprehension complete the circuit, bringing the design to life in a new and profound way? Contemplating consciousness brings our journey full circle. We began by searching for the hidden plans of the universe, and we end by finding ourselves written into them, not as passive inhabitants, but as the means by which the cosmos becomes aware of its own existence and its own elegant, mysterious design. Galileo's simple spyglass cracked open the sky, revealing moons around Jupiter and forever changing our place in the cosmos. Each leap in our understanding has been propelled by a similar revolution in our tools, a sharper lens through which to read the universe's faded plans. Today, a new generation of instruments is coming online, each designed to probe a different layer of the cosmic blueprint with unprecedented clarity. The James Webb Space Telescope acts as a time machine, its infrared gaze piercing the cosmic dust to witness the birth of the very first stars and galaxies. It sees the universe not as it is, but as it was in its infancy, observing the moment the primordial architecture first began to glow with starlight. Meanwhile, the Vera C. Rubin Observatory will perform a relentless 10-year cinematic survey of the entire southern sky. Its enormous camera will capture the motions and changes of billions of galaxies, mapping the dark matter scaffolding of the cosmic web in greater detail than ever before and potentially catching fleeting, explosive events that rewrite our models. But to truly feel the vibrations of the cosmos, we must listen. The LISA mission, a space-based gravitational wave observatory, will detect the low-frequency hum of merging supermassive black holes, events so colossal they shake the fabric of spacetime itself. This will allow us to hear the universe's deepest, most resonant notes, a symphony of gravity that has been playing since the dawn of time. We are also building eyes that can see through solid matter. Gigantic neutrino observatories, buried deep under Antarctic ice or in the depths of the Mediterranean Sea, capture these ghostly particles that fly straight from the cores of collapsing stars and the furnace of the sun. They offer a direct, unedited view into the most violent and energetic processes in the universe, and deep underground, in abandoned mines and tunnels shielded from cosmic interference, the hunt for dark matter continues. Ultra-sensitive detectors wait in profound silence for the hypothetical bump of a WIMP, while particle colliders strive to create new forms of matter that could reveal the hidden sectors of physics. Each new tool is like a new sense granted to us, revealing a dimension of the design we were previously blind to. What subtle signatures, what hidden clauses in the universal contract will these technological marvels finally bring to light? The blueprint is not getting any younger, but our ability to read its finest print is just beginning. The elegance of these cosmic laws points toward a realm beyond simple matter, a domain of pure mathematical relationships that seems to pre-exist our physical reality. This idea echoes the ancient philosophy of Plato, who proposed that the world we perceive is just a shadow of perfect, eternal forms. The equations of general relativity or the symmetries of quantum mechanics feel discovered, not invented, as if we are uncovering truths from a timeless, abstract landscape. This Platonic perspective suggests the blueprint was not drafted at the moment of the Big Bang, but has existed forever in a conceptual space, waiting for a universe to instantiate its perfect logic. Yet this view is challenged head-on by the sheer randomness implied by the multiverse. If an infinity of universes bubble into existence, most of them sterile and stillborn, then our exquisitely tuned cosmos loses any claim to special design. It becomes a statistical fluke, a lucky ticket in a cosmic lottery with nearly infinite losing numbers. This forces a difficult choice. Do we live in a universe that appears uniquely crafted because it genuinely is, pointing toward some form of cosmic purpose? Or is our presence merely the inevitable outcome of a blind, prolific process that was bound to produce a handful of habitable worlds? The reductionist answer is powerful in its simplicity, arguing that everything from the rotation of a galaxy to the firing of a neuron is ultimately the consequence of particles obeying fundamental physical laws. In this view, the blueprint is all there is, and concepts like beauty or meaning are just ephemeral byproducts of complex chemistry. But an emergentist perspective pushes back, insisting that new levels of reality bring forth genuinely new laws and phenomena. The rules of biology cannot be fully deduced from the equations of quantum physics, just as the laws of economics cannot be predicted from the principles of chemistry. Consciousness itself emerges from the brain, yet it feels undeniably real and central to our experience. So where does that leave our search for meaning? If the universe is fundamentally mathematical, is the beauty of a sunset or the depth of human love just an illusion? Or are these experiences a different, equally valid way of reading the blueprint, a translation of cosmic structure into the language of feeling and awareness? The blueprint does not give us easy answers, but it frames the ultimate question. Are we temporary patterns in a vast, impersonal machine? Or are we the universe's way of becoming aware of its own breathtaking design, suggesting that meaning is not something we find, but something we create and live right here within the grand architecture? Each separate clue we have uncovered is a stroke of genius in a single, vast masterpiece. The faint ripples in the cosmic microwave background are not an isolated fossil. They are the direct genetic code for the great cosmic web, whose dark matter filaments were shaped by those primordial seeds. The relentless push of dark energy is not a separate force, it is the counterbalance to gravity's sculpting hand, a dynamic tension written into the initial conditions. And the bizarre rules of the quantum realm must ultimately connect, stitch by stitch, to the smooth curvature of spacetime described by Einstein. Our quest is to weave these individual threads into one coherent fabric, to understand how the universe's largest structures and its smallest particles are bound by the same fundamental architecture. This synthesis is the ultimate act of cosmic cartography, an attempt to draw a single map that charts everything from the brief, violent frenzy of inflation to the slow, cosmic dance of galaxy clusters. It requires us to reconcile scales that defy human intuition, connecting the frantic uncertainty of a quantum fluctuation to the stately, deterministic orbit of a planet. How does the holographic principle, suggesting a two-dimensional source code, generate the three-dimensional reality we navigate every day? The answers lie at the intersections, in the mysterious bridges between these disparate domains. This is not just about collecting more data, it is about finding the narrative that makes all the data make sense together. We are searching for the story that explains why this particular combination of forces, constants, and initial conditions resulted in a universe that could eventually ask questions about itself. Every telescope peering into the deep sky, every particle collider smashing matter together, and every theorist scribbling equations is contributing to this grand collaborative project, humanity's collective effort to read the master plan. We are assembling the ultimate schematic, one where the blueprint for a quark is inseparable from the blueprint for a galaxy, and where the entire cosmic cathedral reveals itself as a single, breathtakingly unified whole. Our journey through the cosmos has been an exploration of a grand design, a search for the lost blueprints hidden within the first light of creation, the invisible scaffolding of dark matter, and the mysterious push of dark energy. Each clue, from the faint ripples in the cosmic microwave background to the vast filamentary web of galaxies, points toward an underlying architecture governed by elegant and profound mathematical principles. We have followed the trail from the quantum jitters of inflation to the holographic suggestion that our reality may be a projection, and even to the possibility of a multiverse, an infinite cosmic library of alternate designs. The true nature of dark matter remains a tantalizing secret, and the original trigger for inflation is still shrouded in mystery. Yet, with every new telescope, every deep underground detector, and every brilliant theoretical insight, we are steadily assembling the pieces of this magnificent puzzle. This search for the hidden design is far more than a scientific endeavor. It is one of humanity's greatest intellectual adventures, a testament to our unique capacity to look up at the stars and ask how and why. We are not just inhabitants of this cosmos, we are its consciousness. As Carl Sagan so eloquently put it, we are a way for the cosmos to know itself. Let this exploration be a starting point for your own curiosity. The universe's blueprints are open for interpretation, and the next great discovery could begin with a single question. Share your thoughts on these cosmic mysteries in the comments below, and subscribe to continue this journey of discovery together.